So what I'm going to talk about now is MPI internals. This is a bit difficult because, of course, as I said before, MPI is a high-level definition, but you need to have some idea of how it operates to understand performance. And so I'm not saying that these statements here are 100% correct, because who knows, but they're representative of what a typical MPI library might do. And luckily, we have some people at EPCC who have in the past developed MPI libraries, so we have some background as well. So I'll talk a bit about the library structure. I've talked about it already, but I'll reiterate it. I'll spend most of my time talking about collectives. Really, that's really, sorry, about point-to-point. I will talk about collectives and very brief about groups and communicators and single-sided, but it's really point-to-point, which is the important thing, which is the fundamental building block of MPI send and receive. So I said here, you know, like any large software package, MPI implementations need to be split into modules. MPI really has a kind of natural decomposition based on the chapters of the standard point-to-point collectives, groups, topologies, process creation, one side, and MPIO. But we said before there'll be hidden internal modules at lower level. So this ADI, abstract device interface, encapsulating the hardware-specific information, which is below the level you care about for functionality, but for performance, you need to know about these things. So point-to-point is the core of most MPI implementations. Collective, of course, are usually, but not always, built from point-to-point. As I said, by default, your MPI library will have implementation of the collectives using point-to-point, but hopefully there may be more efficient implementations taking advantage of particular hardware characteristics. MPIO is typically built on standard communications libraries. Very early on, I'm not going to cover MPIO here, but very early on, someone implemented MPIO using pure MPI. So Romeo is the typical implementation. But there's a large number of point-to-point calls that exist, but these are often built up from simpler core sets of functions. And okay, so I don't want to be preaching to the converted, but you know, we want a simple performance model, and this is how we're going to characterize point-to-point performance. And I like to use analogies. I'm really not a fan, but they make great analogies. So the analogy is a car journey. My car is parked at a nearby garage. It takes 5 minutes to walk there. After that, I average 60 kilometers an hour when driving because I get straight onto a main road. So how long does the journey take? What is my average speed? So what we would do, we could plot the time taken for a journey against the distance. And we would see two things. We would see a constant slope, because the time, because I'm going at constant speed, the time is proportional to the distance. However, there's an initial overhead. And in MPI, we would call this the latency. It takes 5 minutes to do anything, okay? And then it takes an increasing number of time to go somewhere. Or I could plot this on a log plot, which is what people more typically do, and it looks like this. So it looks very flat. So you have a latency, a finite intercept, and then you see a big increase. So actually, I mean, I don't really like log plots, but anyway, we have to do them to fit things onto the sorry, this is a yeah, sorry, log the time against a log distance. Sorry, it's a log linear plot. Sorry, not a log plot. We often, so the reason we have to often do log plots is in MPI, this x-axis would range from bytes to gigabytes possibly. So we have to do a log. So it's worth noting that although that looks like a rapid increase, it's actually a linear graph. But that's just an analogy with a car journey. Okay, a latency of 5 minutes to do anything. Okay. And after that, a constant speed. And the obvious analogy is, so for the small and large distance behavior, small distances take constant time of 5 minutes, okay? So if I plot the time against the distance, okay, small distances take a constant, what looks like a constant, pretty constant time of about 5 minutes, okay? Whereas if I plot the speed, okay, I only get a constant speed of 60 kilometers an hour when I achieve a long distance. And you might then say, well, what's a long distance? What's a small distance? Okay. Well, I would say a long distance was one where you spend more time driving than walking to the garage. Okay. And this is called n.5, equal driving time as walking. Okay. When the latency is equal to the journey time, that's kind of what you call a modest size message. So the n.5 is 60 kilometers per hour times 5 minutes is 5 kilometers. In other words, if I go less than 5 kilometers, I spend more time walking to the garage than I do driving, and I will, I'm dominating. I'm in this region, I'm in the small message region, where effectively it's a constant time of 5 minutes. But for large journeys, much bigger than 5 kilometers, I'll be achieving constant speed of 60 kilometers an hour. So that's just an analogy. Car latency, 60 kilometers an hour, small or large distance. Clearly, for point-to-point MPI, the latency is the overhead of sending any message, and some time to get a very short message onto the network. Now, actually, the latencies are quite high. It's often a software latency or an OS latency. Basically, modern processors, computers, operating systems are very shrink-wrapped. That makes them robust. But here we want to do something quite nasty. We want to get data from our process out onto a physical network, which is a different piece of hardware outside of the operating system, and that is tough. Okay? It takes the time, and typically it's measured in the microseconds. We'll do some measurements later on, but think of order microseconds is the latency. The bandwidth, so that's the walking to the garage. That's how long does it take to do anything. The bandwidth is the rate of transfer on the network, which might be something of the order of tens of gigabytes per second. So with these parameters, n.5 is 10 kilobytes. That's saying that for these parameters, and these are typical, but we'll see what they are on ARCHER2, messages less than 10 kilobytes are small. They're dominated by the latency. They'll take an order a microsecond. Messages much larger than 10 kilobytes are dominated by the latency. You'll get a fixed bandwidth, and so that is an interesting point. It's worth knowing when you write your MPI program. Am I sending small or large messages? Am I dominated by the latency or the bandwidth? And unfortunately, most programs tend to be dominated by the latency, and latency is actually the hard thing to get down. It's very easy to get extra bandwidth. You just add two network interfaces. You have two lanes, okay? But it's easier to get bandwidth. But it's the latency which is the killer often. And most MPI programs typically send messages which are quite small. And in particular, if you think about an all reduce, you're doing an all reduce on a single double precision number normally. So we're way down in the latency level. So that was just is that clear? I wanted to sort of and we'll get these graphs for ARCHER2 in a second. So yeah, David, you had a question?
Sorry, no, I was looking for a yes button. Yes.
Ah, okay, that's fine, no problem. That's fine. So MPI communications, there are multiple. So this rest is it's just a general concept. I'm just saying that if I owned a car and someone said, "Do you do small or large journeys?" I'd say, well, 5 kilometers is a small journey, because at that point I spend more time walking to the garage than I do driving. Much more than 5 kilometers is a large journey, because the overhead of 5 minutes walking to the garage is irrelevant if I'm driving to London. It's the same thing. You're saying so we want to know, are you dominated in your program by latency, of the latency of the network or the bandwidth of the network? And actually, this is a big question for going out to buy a computer. Should you buy a computer with a small latency and a large bandwidth? A small latency and a poor bandwidth, or spend your money on trying to get a low latency? And so the question is, is my program sending small or large messages? Are they dominated by latency or bandwidth? Well, this n.5, which is the latency time to transfer rate, gives you that crossover point, roughly. Does that make sense? And if you do a log plot, you'll see actually that's at the point at which you see it shooting up. You see, this is this threat, this latency dominated behavior, fixed time, bandwidth dominated behavior, fixed. Dominated by the bandwidth, we get a fixed bandwidth here. So you can see that this crossover, and this n.5 is a useful, where you spend half your time in latency and half your time in bandwidth, a useful concept. So MPI defines too many types of send. We've talked about buffered send, complete locally, whether or not a matching receive has been posted. The data is buffered somewhere, typically on the sender. until the receiver is posted. Buffer send fails if insufficient buffer space is attacked. Synchronous send can only be complete when the matching receiver has been posted. But we also saw that we have ready send. Again, this is one of the historical things. I've deleted this from my normal MPI course. A ready send actually requires the receive already to have been posted. You should never use it because it's almost impossible in MPI to guarantee if you have a sender and a receiver, the receiver has posted their receive. You see, if you knew a receiver was already posted, clearly you could optimize this. If you know a receiver has been posted, then when you send a message, you can just send it. You don't need to ask, are you ready for this? But it's really historical anachronism. One of the early message passing paradigms must have had a ready send, where the receiver is ready to receive. And if the receiver isn't ready, then all hell breaks loose. You should never use it. But standard send is the one I should concentrate on. Standard sends may be either buffered or synchronous, depending on the availability of buffer space and which mode the MPI library considers to be the most efficient. And application programs should not assume buffering or take completion as an indication the receiver has been posted. What I mean is, if you call MPI send, when it returns, you don't know what's happened. It could have been buffered locally, or it could have been delivered. You don't know which. But the point is that's deliberate, so the MPI can decide what it wants to do. And what it will do is typically buffer small messages, but use synchronous, wait for the receive to be posted for large messages. And so MPI requires quite a bunch of things to be true. MPI requires ordering of messages. So all of these things are things you may not ever have thought of, but they do place quite strict requirements on the MPI library. Messages sent between two endpoints must be non-overtaking. Receive calls that match multiple messages from the same source should always match the first message sent. Actually, if you think about it closely and cleverly, you make almost any MPI program you write requires this to be true. If I send a message and then send another message, if they arrive in a different order they were sent, then all hell, your program, it's very hard to write a working program if that isn't true. But it's difficult to implement because at the network level, at the hardware level, the packets will overtake each other all the time. So this is something the library developer has to worry about. MPI doesn't guarantee fairness. For example, if you have a lot of non-blocking receives, so we'll come back to the advantage of buffered send using asynchronous. So this is what's the advantage using buffered send compared to asynchronous send? In MPI, so MPI speak is a bit confusing. Buffered and asynchronous are the same thing. Do you mean buffered versus non-blocking? I send, for example. So that's I'm trying not to be pedantic here, but yeah, okay. I would say don't ever use bsend. MPI programmers don't tend to use bsend because it's nasty. You have to basically provide the buffer space yourself. You're saying to MPI, you must buffer this message. Okay. The MPI party line is, don't tell me whether I should buffer or not, use send. Okay. But then you have the problem with, if you use send, if MPI decides to be synchronous, then it could deadlock. So you should use, if you have a choice using bsend, I would say use isend, because isend has two advantages. A, it avoids deadlock because it's non-blocking, but B, it still gives MPI the freedom to choose how to implement the send. So although they achieve the same thing, point-to-point message passing within the absence of deadlock, isend is the recommended thing. I very rarely see people using bsend, I have to say. So yes, you can use tags for matching sends and receives, but actually in MPI you very rarely have. So yes, if message ordering was not guaranteed, you'd have to use tags all the time. You'd have to tag every message. But actually, most MPI programs don't require tags because of message ordering. And actually, I'll come back to this later on. But you're right, we can use tags for matching sends and receives, absolutely. MPI doesn't guarantee fairness. If I have 5 non-blocking receives outstanding and I say, could you complete one of them? It could always complete the one to the, but good MPI implementation will be fair. Resource limitations, there should be a finite limit on the resources required to process any message. That's why MPI cannot guarantee to buffer every message, because that you'd have to it would have to have an infinite number of resources. And progress, we'll talk about this later on, but outstanding communication should be progressed wherever possible. This is an interesting one, and this is where MPI doesn't behave like you think it does, and I'll talk about progress later on. These influence the design of MPI implementations. So message progression, here it is. This is a slightly contrived example which illustrates MPI. What I would probably rather do is use this one for message progression. I will. Okay, so that is a bit contrived. I can come back to that, but I'll illustrate it with a different example here. So MPI defines both blocking and non-blocking calls. Actually, low-level network protocols are actually likely to be non-blocking. Now, async MPI says no. Other people use the word asynchronous for non-blocking. MPI differentiates it. It's a bit confusing, but most implementations will implement blocking messages as a special case of non-blocking. But anyway, while the application may be blocked, the MPI library still has to progress all communications while the application is waiting. Okay, so and obviously, if as a library developer you've only implemented non-blocking, effectively map onto a non-blocking send, receive, and await. That's fine. But non-blocking is a very good way of programming, but it has certain certain complications. Here's this example. Okay, so I'm doing a halo swap. Okay, so I post an I receive from my up neighbor and an I receive from my down neighbor. So these are non-blocking. Okay, so they return requests, which are my handles, my tickets. Okay, I then do a synchronous send. Okay, to the down neighbor. Okay, now imagine, okay, that my down neighbor is not ready yet. Okay, so what I could do is I could say, well, I'll do nothing. Okay, but wait until that receive is posted. Okay, yeah. But my down neighbor might also be doing a synchronous send. What I'm trying to say is, if everyone says, okay, if everyone sits in the synchronous send saying, I'm going to wait for my neighbor to be ready, okay, then the program would deadlock, although this is a correct program. So what I'm saying is, although you've called the synchronous send, which is, please could you, don't deliver this message until the receive is ready. What MPI has to do is, it can't just sit there. It has to say, well, okay, you want me to do a synchronous send. You want me to, but I've also got these outstanding non-blocking receives. I better process them. Okay. So although you think MPI is sitting there in synchronous send, waiting for the receive to be ready, what it's actually doing is taking the opportunity to progress its local things. There's lots of stuff going on in MPI, and so what it will do is, although you think it's sitting in this call here, it will also be progressing these non-blocking calls. Without that, the whole program could deadlock. So what MPI, the important point is, MPI is written to be single-threaded. You think of MPI as this engine which runs in the background, but that's not how it works typically. The only time MPI can do anything is when it's in the MPI library. So when you call an MPI routine, the first thing MPI does is, it doesn't do what you want it to do. It goes away and progress. Okay, David wants me to do synchronous send, but I better go away and check what else is going on. Oh, I've got a non-blocking receive. Has anything come in? I've got a non-blocking send. I've got lots of other stuff to do. And so, if you think about it, and we need the waits to clear out, while you're in these synchronous operations waiting for stuff to happen, you have to get on with other bookkeeping, which is called progression. You progress other outstanding communications. So the important point is, when you ask MPI to do something, the first thing it does is probably go and it's called the progress engine, keep other things ticking along. Because although you might like to think MPI is a universally running library that's running on a separate thread, that is probably not true. So that's a slightly complicated example, but that's the important point, is that MPI effectively uses every MPI call that you make as a manual interrupt to go away and do other stuff. Okay. The other reason why I wanted to use this example is that you'll see that this is related to message ordering. I've posted a receive to my up neighbor and a receive to my down neighbor, and I've sent to my down neighbor and sent to my up neighbor. Okay, that seems like the right thing to do. But what happens if there are only two processes? So your up neighbor and your down neighbor are the same thing. Okay, so I'm wanting to. So if I'm rank 0, I'm receiving from rank 1 and rank 1, and then sending to rank 0 and sending to rank 0. Okay, so imagine your up neighbor and your down neighbor are the same process. Do you think this code works? Does it do the right thing? Does this send to the down neighbor match this receive as it's supposed to? Do people think it does or doesn't work? And in the general case, this code is fine because your up neighbor and your down neighbor are different, and so there's no ambiguity. This receive from your up neighbor is different from this receive from your down neighbor. But if you're in a small system where you maybe only have two processes and your up neighbor and your down neighbor are the same person, okay, I'm issuing two receives from the same process and issuing two sends to the same process. Will they match up correctly, assuming we're not using tags? It's a bit of a subtle question, but the answer is they will, because I've been careful that I've issued the receive to the up first and the send to the down. So this send, okay, yeah, the order matters. This send to the down neighbor matches this receive because that one was posted first. When I do this send to the down neighbor, it matches two of the receives that the down neighbor has posted, but it will match the correct one because my neighbor posted their up receive first before their down receive. So sometimes people aren't careful. They'll do MPI receive up, MPI receive down, MPI send up, MPI send down. That will work in most cases because there's no ambiguity, but it will fail for small system sizes because there is an ambiguity. Now you could fix this with tags. You could tag your up messages with 1 and your down messages with 2, but actually message order preservation saves you here. So message order preservation is actually quite powerful. Persistence, we'll come back to this. The MPI standard also defines communications. They're like non-blocking, but they can be really run multiple times. Now, the advantage here is that every time you issue a send call or a receive call, MPI has to do some checking that the parameters are valid, like the rank is valid. So, however, actually, those are very low overhead. So the rationale is if you're going to do a send operation many times, you say to MPI, look, I'm going to do this send operation. I'm going to send the X buffer with 100 integers millions of times. Could you register that? And then you just say, do it, do it, do it. And I have an example later on. However, actually, the amount of time that saves is minimal. But actually, now we have persistent collectives, which I'm not going to talk about, but you can look them up. Well, they're coming up in MPI4. Persistent collectives are under discussion. I believe that they are actually implemented now, at least in the standard, if not in the implementation. Sorry, they're defined in the standard, if not implemented. There's a lot more optimizations you can do, and so so persistent operations aren't particularly useful for point-to-point, but they will hopefully prove very useful for collectives. Derived data types, MPI defines a rich set of derived data types, and the classic one is something like, in a very simple code, a halo swapping code, often your boundaries aren't contiguous sections of memory. Even in a 2D code, one of the boundaries of your array is going to be a non-contiguous section of memory. You can, of course, do copy into a contiguous buffer, send and copy out, but MPI has derived data types, things called vectors or subarrays, which allow you to natively send non-contiguous data. Now, at the lowest level, MPI is probably doing a copy in, copy out. So it may be quicker to do it yourself, but I would recommend using derived data types rather than copy in, copy out. Copy in, copy out is ugly, and it is possible that the network actually supports strided transfers. So, I mean, this is just the derived data type. There's nothing magic about derived data types. At some level, probably inside the library, it's doing it. It's what you might nowadays call serializing them. But I would still recommend using them for elegance. So I'm just now going to talk about how MPI actually implements send to send. When do we do examples of derived data? So I don't think I'm not going to do derived data types in this course. I cover them in the basic course, talking about vectors, which allow you to send vectors allow you to send strided data, and structures allow you to send, well, C structures or Fortran derived types. So I can talk about them with you if you want, but I'm not going to really cover them here. That's okay. So an MPI implementation needs a method of delivering messages, packets of data to a remote process, and these could be your message or internal protocol messages. So the model I have in my mind is whenever a process sends an MPI message, it has to send an initial protocol message. Must be sent. This is like a header, okay? So minimally, it's just the envelope. If I want to send a data to another process, a gigabyte of data, I would send a little header message saying, look, into some queue on the remote side, saying, look, I've got a message waiting for you. It's coming from me. It's a gigabyte of data, okay? So many implementations use a fixed size header for all messages. So this might be, and we'll see probably what size this is, from maybe 128 or 256 bytes, okay? So whenever you send a message, there will be a protocol message sent, which might just contain the envelope information, but it might actually contain some data. We'll see that later on, which says as a message, here it is, okay? It's like a calling card. So if the receiving process already issued a matching receive, then you can process the message immediately. If the receive is not ready, the message must be stored in what's called a foreign send queue. So basically, if you get an unexpected message, you don't have an outstanding receive, while you're hoping there's a receive later on, so you have to stick it in a queue saying these are incoming messages which have been posted that I haven't issued a receive for yet. And also, if you have a receive call, you'll look for matching messages in the foreign send queue. Okay, so if you issue a receive, okay, you might say, actually, well, has a message already come in? Oh, yes, it does. I can process it. If not, I have to pend it and say, look, I'm expecting a receive, but it's not come in yet. So there could be lots of such queues for different communicators or senders, but typically we have a single set of global queues. Now that is a performance bottleneck, as you can imagine, on very large systems where you have millions of MPI processes. One of the problems, these queues can get huge because they have to be able to store messages from lots and lots of people. But it makes wildcarding. Wildcarding is quite difficult for MPI to cope with, and people have actually suggested taking it out. But if you have a global queue which includes all the messages which are outstanding, it's much easier to implement fairness, progress them in a fair way and look for matches in wildcarding and such like. But basically, the important point is whenever you issue a send or a receive, I will first check if you've issued a send, is there an outstanding receive? If not, you have to queue it up. Or when you issue a receive, if a send has already come in, they match. If not, you have to queue it up. So there'll be lots of outstanding stuff going on, all stored internally. So how do we actually send a message when we've decided we have a match and we actually want to send the data? Well, typically the implementation will use different protocols depending on the size of the message. And the simpler ones are eager and rendezvous. So there's many variants on these basic protocols, but these are the two classic ones, eager and rendezvous. So eager, the initial protocol message contains the full data for the corresponding MPI message. What I'm saying is, basically, if you tell me to send data, okay, in the eager protocol, which is clearly only possible for small messages, I basically send all the data. I send a header and all the data at the same time, and then I carry on. So that means that the receiver has to have enough space available to store these unexpected messages, so they clearly can't be used all the time. But for sufficiently small messages, we'll investigate what that threshold is. When you issue send, okay, what will happen is that data will be immediately sent across. And this is, so what MPI send will do is MPI send will say, if it's a small message, I will do an eager send. I will just basically, small enough, I can send all the data immediately over to the receiver, and then I can just carry on, okay? The eager, so this means that buffered or standard sends can complete as soon as the initial protocol message has been sent, okay? So if you have synchronous send, then you have to, synchronous send requires you to, has an acknowledgement for completion. So you have to have an extra message coming back. Although you might send the data immediately, you still have to wait till the receiver has been processed. That's a slight technicality. But the main point to think is that this is what MPI send does. It says, if the message is small enough, typically below maybe a few tens of kilobytes, I know that there's enough receive space on the receiver to send the data immediately. I'll implement it in an asynchronous way, buffered way, send the data over and just carry on. So that's why small messages tend to be sent quickly, because they can just be sent over. You can fire and forget. However, the eager protocol clearly requires buffering the receiving process. You can't always do eager, because that would violate the requirement that you have a finite number of resources. I'm not going to talk about ready messages here. I mean, I said you should avoid ready send. It's not something which I would recommend using. So what happens if I say, I want you to send this message gigabyte? Well, clearly there's no way I can guarantee the receiver has a gigabyte of message. So what I do is I send an initial protocol message, which is just a header, okay? It's no data. So I just say, look, I've got some data I want to send you. Get back to you when you're ready. When this is matched, then the receiver gets back to me. So eager is one way, fire and forget. The rendezvous protocol for large messages is you send a protocol message across. When the receiver is ready, they'll get back to you, and then you send the data. So it's there, back, and again. So the sending process, so what happens is you just send a protocol message across. Then when the receiver is ready, it says, I'm ready. Then you send the data in a new message, a new low-level message. To the MPI program, it's all one message, but it's split into two parts. So in this case, sends acts as synchronous send. It waits for the matching receive. So that's when this is basically a send is synchronous. It waits for an acknowledgement, and so that is why for large messages, MPI send will use the rendezvous protocol, and then it becomes synchronous. In other words, it doesn't return until the message has been delivered. You might think that that means that the rendezvous protocol is always slower than the eager protocol, but that's not true. For very large messages, rendezvous can be quicker because it doesn't require any buffering. Because basically, with the eager protocol, you have to copy in, copy out. With rendezvous, in principle, if someone gets back to you and says, I'm ready for the data, you can then copy the data directly from sender to receiver without any intermediate buffering. So although for small messages, eager is quicker, you have to switch to rendezvous for intermediate sized messages, which will introduce an overhead because there's more handshaking going on. For very large messages, rendezvous can actually be quicker than eager. So there are trade-offs. So when we look at MPI performance, we typically see thresholds. We look at the time to send a message against the size of the message. We might see different thresholds, where here this is the small message eager threshold. Then we see a jump because of the additional overheads, and then we see a lower bandwidth. Well, we see two distinct regions: low message size and large message size. And if we saw this behavior for MPI send, we could infer that this is the point at which it's switching from eager to rendezvous, and hopefully we'll see that when we run the exercise. Other protocol variants will actually, for very short messages, for very short messages, you could actually stick them on the protocol. The initial protocol message typically has a size, maybe 256 bytes. If you're only sending a single double precision number, you could send the protocol message and say, actually, the data's on the protocol message. I think of this as sending a postcard rather than a letter. If I want to send a letter, I have to write a letter, put it into an envelope, seal the envelope, and send the envelope. If I have a very small message and I'm on holiday, I just want to say, having a great time, I use a postcard where the data is included on the envelope, the postcard. And so, you don't have to open it, it's just there. So we might even see three regions: large messages which uses rendezvous, small messages which use eager, and very small messages where actually all the data is sent on this single included in the header. For very large messages, you may be able to do direct memory access, but which is direct memory-to-memory transfers over the network, but that requires a very large setup cost, and typically that's only reserved for very, very, very large messages in the gigabytes. So in practice, it's not relevant, and we probably won't get to that limit for our exercises today. A brief statement about collectives. I've talked about this basically. Collective routines are sometimes built on top of point-to-point. You could re-implement themselves, but even if they're built on point-to-point, hopefully they'll use a very optimal algorithm, and the algorithms are quite complex and non-intuitive. So you should always use collectives, even if you know that the implementation is using point-to-point under the hood. You should use collectives. But as I said, there's nothing in the API that requires this. Barrier synchronization may be supported in the hardware broadcast, multicast. Shared memory nodes, you may be able to do direct memory copies on a shared node. So you can imagine that if you're doing a broadcast, the most efficient way to do it is to use a hardware broadcast, for example, across the network. And I'll come back to that question. And then locally, only to one process on each node, and then you do memory-to-memory copies. So I wonder how the sites that decide to qualify for eager rendezvous postcard protocol, they will be tuned by the library developers to match their network characteristics. So we'll come back to that. So yes, you're absolutely right. You have postcard eager rendezvous protocols with thresholds, and you hope that the vendor has tuned those thresholds so that they're optimal for their network. However, of course, they're never completely optimal because different programs are different. So we'll come back to that. It's a very good question. Well, now yes, exactly. So it's a pragmatic decision. They have to be constant. But for example, if you know that all your messages are 20 kilobytes and the eager threshold is 10, you might like to increase that threshold, and you can do that. But it's sort of black magic via environment variables. We can come back to that. Collective algorithms. I'm not going to talk about these, but typically they're done in a tree-based fashion or hyper. The main point is that the time taken for a collective algorithm typically grows as the log of the number of processes, whereas a naive implementation, which you might do, would grow linearly with the number of processes. So that's done through clever tricks such as tree-based algorithms and such like. But all I really want to say here is that people put a lot of effort into implementing these algorithms efficiently, and you should use collectives whenever you can. But typically, you would hope that for a well-implemented collective, it will scale logarithmically with the number of processes rather than linearly. In MPI, we have communicators. Communicators separate communications domains. So in that trick question I had about all reduce, if you had wanted to do an all reduce, so the all reduce, if you had wanted to do an all reduce separately on the even processes and the odd processes, you would have had to put all the even processes in an even communicator and the odd processes in an odd communicator, and then call the MPI all reduce on the even communicator or the odd communicator. So MPI allows you to divide processes into subgroups by creating new communicators. However, at a hardware level, that's a logical part. At a hardware level, you just have lots of CPU cores. So logically, communications are independent communications domains, but actually, well, most applications use very few communicators at a time. Most MPI implementations at the lowest level in the ADI will use a native processor. In other words, the same as MPI ComWorld. When you send a message, you'll just send a message to a particular process, okay? Process 95. However, that message could be sent in different communicators. That will be encoded through some hidden tag, okay? So, at the lowest level, there'll be some hidden tag which actually says, this message is for you, but remember it's been sent in this communicator 7, not ComWorld. So just to say that, the communicators are a high-level concept. At the lowest level in the MPI library, it probably just sends messages and encodes the communicator in some hidden tag, which you don't see. Okay? So I mean, that's, you know, that's how it's implemented. There's nothing magic about it. You should use groups and communicators yourself, but at the lowest level, there's nothing magic about them. It's just probably encoded as an extra tag saying what communicator it's in. And MPI does assume you use very few communicators at once. If you start defining thousands of different communicators, MPI can sometimes get unhappy. Process topologies, you may not have used them, but MPI allows you not just to create subcommunicators, also to say to MPI, see these 100 processes I have. They're not just 100 processes, they're actually arranged in a 10 by 10 2D grid. So you can actually tell MPI that your processes are in a grid. And in principle, this allows MPI to place your processes or number your processes more efficiently. It can say, well, David has got a 2D decomposition of his processes into a 2D grid. That doesn't map very well onto the physical network topology, so I'll do a logical renumbering of his processes at runtime. Actually, so that's deliberately there in MPI to allow MPI to optimize your communications at runtime, but actually most don't do a good job. Process topologies are nice if you have regular grid communications. You should try and use things like MPI Cartesian topologies. At the moment they're a bit of a convenience for reasons I could come back to, but actually process topologies really come into their own with neighborhood collectives, because there the communication pattern is in, so you can, there's a single routine to say I want my process to exchange data with all its neighbors, and because you have told MPI that your processors are in a 3D grid, it knows who your neighbors are. It knows your 6 neighbors are up, down, left, right, forward, backwards in 3 dimensions. So I'll illustrate neighborhood collectives with an example. But currently, if you just use point-to-point communications, process topologies, which are the most fundamental like Cartesian topologies, are useful and elegant, but not particularly impact on performance, but they've really come into their own when you use neighborhood collectives. Single-sided, I've talked about this now, but I'll come back to this tomorrow, but just to flag it up, I've already memory windows replace communicators, and you have remote write put and remote read get, but they're really quite complex, slightly ambiguous in place. It gets very complicated for many applications. Single-sided performs slower than normal point-to-point in MPI2. The MPI3 has tried to clean that up, but the most important point about the MPI3 single-sided interface is that you can directly read and write to memory windows on a node. In MPI2, you could create shared memory windows between processes, but you needed to call function calls put and get to read and write to them. That seems crazy if 2 processes are on the same node. They physically share memory. In MPI3, and I will cover this on Friday, you can define shared memory windows and directly read and write to them with memory reads and writes. In other words, you can have the equivalent of OpenMP shared arrays in MPI, and I think that's quite powerful. So I will cover that on Friday. The summary is, there's many ways to specify MPI communication, probably too many. Which one is best depends on the implementation, which MPI library you're using, which hardware you're using, which options you're using. Performance portability is hard. It's hard to know what's fastest. I would recommend implementing lots of methods and testing them, and we'll do that in a subsequent exercise. I have a program which implements halo swapping in a dozen different ways. But what we're going to do next is we're just going to run a simple ping pong example. So if you go to the website, we should have the exercise. Oops, I've done the wrong thing. Apologies, it's not very clear. sometimes which window. Oh, I'm really sorry about this. I'm sharing the wrong window because I'm being very stupid. ARCHER2 AMP. Sorry about this. Kevin's put the URL there, but fine. So how's it work? Yes, here we are. So if you look at the exercises down here, so the way I'll go through this, but basically here's the ping pong exercise sheet that may or may not render in line depending on your browser. Oh, it does. Okay. So hopefully that gives you the exercise. It's quite a short exercise, but sorry, quite a short exercise sheet, but hopefully illustrates a lot. There's the source code. What I would recommend is to get the code onto ARCHER2. I would copy that. Now, you could git clone this entire repo. I don't see why you shouldn't do that, which would give you all the slides and everything. But I would recommend basically copying that link, okay, and then on ARCHER2, so hopefully you can see now, you can see in my window, this is me logged onto ARCHER2. Whoops. So when you log into ARCHER2, you will start off in the home directory. The first thing you should do is to cd to the work directory. You cannot run parallel jobs from the home directory, unfortunately, on ARCHER2. It's a bit of I have a strange username here. I'll get rid of the ping pong code, which I have already here, and you can just use wget. So you should be able to just wget across that app. And I've just cut and pasted the URL from the website, and because if you download it, it will download it to your laptop, and you have to SCP it to ARCHER2. So you should be able to wget by just cutting and pasting that URL. You should just be able to wget directly onto ARCHER2. Okay. Then, if you see, we have a bunch of stuff here. We actually have this ping pong.tar. I'm very old-fashioned. I use tar files. You unpack it, and then we cd into ping pong, and then we have the exercises there. And you should just be able to make, and you should just be able to queue sub the job. But as I said, we have dedicated queue. So I would actually say that so by default, this is running in the short queue, which is available all the time, but there's instructions on the website on how to I'll cut and paste them. And I haven't been able to test this because the reservations, but it should work, is that I should be able to do, instead of that, this, okay, I should be able to queue sub that. So I should just be able to queue sub archer2.job. Sorry, not queue sub, sbatch. Whoa, so we do sq minus $user, which is me, it is running. Shouldn't take more than about 20 seconds to run, hopefully. Yeah, it's finished now. And what you will see is some output. There's an error file, which is thankfully empty, and a log file. So if I look at that log file, you will see it says 1,000 ping pongs from 1 integers took this. It does lots of ping pongs, okay? But that's not particularly interesting. We have graphs for these. But the most important thing is that it says where the processes are running. So it says running on 2 processes, sending messages between ranks 0 and 1. Rank 0 running on core 0 of node this. The important point is I'm running 2 processes. They're on different nodes, so I'm communicating across the network. And you can see that that's determined by the job file, because I'm saying I want 2 nodes, but I only want 1 task per node. So that, now, we can vary that, and the exercise sheet tells you how to vary those. But the MPI, the program, prints out where these things are running. So for example, you should be able to tell whether you're running ping pong on one node or on two nodes. And slightly more subtly, if you're running a ping pong on one node, the one node actually has two processors. Are you running a ping pong between different processors on the same node or within the same? And that will give you different numbers. So I would just give people a few minutes. I'll maybe go through the answer to the exercise at the end. But if somebody doesn't have any, I don't know if anyone has any questions. I haven't seen anyone come in. But my plan is that you should work on the exercise now. I'll be here to help you. Hopefully that should work out the box like it did for me. But we can look at the answers. I think you use GNU plot to look at the answers. I may not have. Yes, that's working for me. So yeah. So I would just, maybe I'll be online for until 1. If you have any issues, please contact us. So I'm expecting you to be doing the exercises now, but I will come back at say maybe in about 25 minutes, and I will go through I will discuss the answers with you on the screen. So I'm just going to take a quick break now, but my expectation is that you'll be doing the exercise now. If you have any problems logging on, get in touch with us. And I will be back to speak to you about 1:45 to Okay, so apologies for the typo in the sheet. I had to refactor the sheet for ARCHER2 and made that typo. Sorry about that. What I was going to do was basically go through the results now. So, I mean, if I do if I plot the time, we see a number of interesting features, and I will share that now. I'm going to do a lot of window swapping here. I don't like sharing my entire screen because this is recorded and it's very easy to inadvertently share something which I shouldn't, email or something, and then we have to edit the video. So I will try and do these things. So this is the plot you should get by default if you run on as I described, as distributed with two processes on two different nodes. Now, first of all, I would ignore this initial point. I think the first time you call MPI, it's doing some setup. So I think this is spurious. The initial very high time is spurious. That's like a warm-up time. So I would ignore that. But we see a number of interesting features, okay? And this shows this ping pong program. I mean, could be written in 10 lines. It's longer here because of the plotting and stuff like that. But this shows an incredible amount of information about MPI. First of all, you can see that, yeah. So the spurious part is actually I've sometimes got it and sometimes not got it. In fact, it might be an error in the no. Yeah, I don't always get it. It's sometimes you get it, sometimes you don't. So it is intermittent. But I think sometimes there seems to be a delay on the very first message. So we see the 3 message regions which we talked about. The very small message region, yeah, under 128 bytes. So that would make me think that possibly the protocol message is 256 bytes, maybe. So you see this initial very fast region. Well, I say very fast. The latency is in the that's a microsecond. So it's a couple of microseconds. So it's still quite it's still a few, but it's in the order of microseconds. Make it a couple of microseconds here, yeah. If I can count the zeros, 1, 2, 3, 4, 5. Yeah, I think that's right. So this is the very small message region where we, as I said, the data can be put onto the protocol message easily. Then this is the eager region where the data is sent eagerly. So we get a slight increase in time, but we see this eager region. And then we get this switch here to rendezvous. And why do we know that goes to rendezvous? Well, you can see that for, this is comparing standard and synchronous. In this entire region here, okay, standard is quicker than synchronous because it's not waiting for an acknowledgement message, okay? So standard is being asynchronous here, which is faster than synchronous, but beyond the eager limit, standard is the same as synchronous. So we get identical performance. So, you know, it shows all the things which I'd hoped it to show, which is a very small message stream, which is very fast, but standard is faster than synchronous because it's using the, and it's not waiting for acknowledgement. An intermediate regime, which is reasonably quick, where again, standard is faster than synchronous because the standard is using the eager protocol, and then a large message regime where standard is identical to synchronous, and you see all those regimes here, and we can see that the latency is an order of a couple of microseconds. So that's sort of what you would expect. Are there any questions about that? Also, I see there is a question here. So yeah, you don't get the spurious initial part. Yeah, fine. So that depends on. Are there any questions about that graph? And I said, it's a fairly simple exercise, but it gives you, I think it gives you a surprising amount of information. Okay, let's quit that. So non-contiguous won't perform better. There will be an overhead. I haven't done. There will be an overhead to the non-contiguous because there'll be a sort of copy in, copy out. I'm guessing. I haven't run that recently on ARCHER2, but there will be. If I kill this and now share the. So what? Well, I'll. Give me a second. This is the bandwidth, and you'll see that we see that we get increase in bandwidth, but this is where up to, this is in megabytes per second. So this is 10 gigabytes per second. So again, we're getting up to almost 10 gigabytes per second at the top here, the graph. And yeah, it's going up to about 10 gigabytes. That's basically our asymptotic level, about 10 gigabytes a second. Now, there are a couple of, for this eager switch, this is where it goes from eager to rendezvous. That is at over 100,000 bytes. That is very large. Normally the switch is down here at about 10K bytes. ARCHER2 is unusual that the switchover happens at a very, very large very large message size. So you would not expect that to be. So maybe you ran on a single node, Giove. Maybe that's the point. Or lower latency. Well, what I was going to do now was I was going to run. So that's over the network. Okay. If I now resubmit the thing, and I'll basically run on. Run on the same node. I'll kill this. So now again, it's got confused. But if I now run on the same node, you see very different behavior and slightly, and I have to admit I'm not 100% sure what's going on here, but the main thing is if you run on the same node, first of all, we're down at the latency is smaller. For standard send, it's sub-microsecond latency. Okay, that's below a microsecond down here, but you see some thresholds. Synchronous is always fast, so on a node, it's using a completely different protocol. You know, on a node, you can do direct memory copies. So, you know, the statements about initial protocol messages and rendezvous are probably not, it's doing something completely different. But the important point is, as you would expect, the latency is much lower. The latency is factor of 4 or 5 lower on a node because you don't need this because you don't have to send over the network. So it's much quicker on it. So communications on a node are quicker. However, it's not particularly important because any real program is going to run on many nodes. You're limited by the slowest factor, which is your message passing between nodes. But you can see here that there are various thresholds. It looks again, well, there's a threshold here at a 1,000, a few thousand bytes, where the standard seems to switch protocol. Again, this might be an eager protocol that for smaller than a few thousand bytes, it can copy directly, assuming the space is there. This could be the equivalent of an eager protocol. That would be my guess. But you don't see the substructure down here. And for some reason, standard is always faster than synchronous. There's no. But I mean, the main thing is it's a lot faster on a node, and it's a different. It's using different mechanisms. If I look at the bandwidth. You'll see that again, the bandwidth goes up higher because you're doing memory copies. It's a few. I mean, this is a few tens of gigabytes, but you have to be aware that here I'm only running 2 processes. They have access to the entire bandwidth. So actually, sending messages on a node isn't free because you're doing copies, and the bandwidth is shared between all the processes on a node. So both of these situations are effectively ideal, where we only have one process active, one sender and one receiver, because in reality, a network connection connects 2 multi-core nodes, and there can be up to 128 processes on each node. So these the maximums you'll ever get. In reality, they will be smaller than this. But if we look at the, can we see anything about the substructure in MPI? What I wanted to say was, if I run on, if I look at the latency was, sub-microsecond for that, but that was just running 2 processes, so they were very close together on the multi-core process. If I put them very far apart, if I actually run 128 processes on a single node, so I do that by saying nodes equals 1 and task per node equals 128, running the same code but just different distribution. I was running out of time, but I'll just show you this. These are things which you should be able to see yourself. So now I'm running 128 processes on the same node. Deliberately, it does a ping pong, not between 0 and 1, but between 0 and 127. So then they're spaced out. And we'll see if we get different results here. We should. So there's a question which I will answer. Yeah, okay, but if you see, that even on a node, you can see this is equivalent, actually almost close to the bandwidth, to the latency across the network. So this is 2 processes on different processors on the node, and you can see you're getting a few microseconds latency here. So you can see that even modern processors are very complicated, and you're getting massively different behavior between 2 CPU cores which are right next to each other and 2 CPU cores which are at different ends of the processor. So that's one of the reasons I put that exercise in there. Nowadays, we used to say communications on a processor is free compared to communications across the network, but as multi-core processors get so big and so complicated, actually latencies within a processor can approach latencies across the network. And so it's a whole different world we're living in, a lot more complicated than it used to be. We had a question here from, Rajesh says, it's very informative to see that every function call is checked for the return error code. is there some way to check if the call never returns? So whoever wrote this program wasn't me, it was a lot better programmer than me, and they checked. Actually, checking MPI return codes is almost pointless, because only 3 things can happen when you call an MPI call. A, it returns successfully, in which case the return code will be MPI success. B, it never returns, as you say, you might have deadlock, in which case you can't do anything. Your program is sitting in an MPI call. It will sit there forever. So you can't check. It's just like any, can I check if a function never returns? Well, by definition, I can't, because it never returns. So that's a bit of a problem. If MPI detects an error, okay, so if you did an MPI receive and the incoming message was too large, the default behavior of MPI is to crash and burn. You can change that. You can make MPI, but basically, when MPI detects an error, it crashes. Your whole program dies. So actually, although you ought to check the return codes of MPI calls, most people don't bother, because if there's an error, it crashes and never returns. So MPI calls either complete successfully and return with a success error code, or they never return, because either they're deadlocked or they crash. So actually, the return code is not much use. If MPI were fault tolerant and it could, then it would be useful. It might say, you've got to, I issued a send, and it might come back and say, well, I wasn't able to do it because the receiving process was dead. But MPI doesn't work that way. So actually, it may not be very pleasant, but the return, other than MPI-IO, which is a different, but for message passing, send and receive, you should check the error code, but actually most people don't, because it crashes and burns if there's an error. Because that's and in fact, if there was an error in an MPI program, it's very hard to know what to do. If it's an MPI error. So yeah, it's a good question, but okay, so hopefully that was useful, and even that simple exercise gave you some insight into how MPI works under the hood. We're going to be coming back now. Oops, sorry, I'm doing something stupid. So the next lecture will be at 2 p.m. PST after lunch. I hope you have a good lunch. And if you type in, I won't be monitoring the chat, I'm going to have my lunch, but if you do type in chat messages, I will see them when I get back. So feel free to type in chat messages here, and I will see them when I get back. And I'll stop the recording now.